right, it is definitely 1:11. Let us go ahead and get going. So before we get going, I should say, let's go ahead and I also want to talk through this domain and range, just this first page, because I was looking at it and I really thought that the idea of this paragraph down here was kind of helpful. So let's say you got this function square root of x minus 3. The domain is all the x values. So in this case, right, we need to set the inside of the square root to be greater than or equal to 0. So right over here, we see, oh yeah, x minus 3 is greater than or equal to 0, which becomes x is greater than or equal to 3. So our domain is everything from 3 to infinity. And we can also see that the range is all the y values that this function has, which is for everything from 0 to infinity. And what I kind of like about this is what Grant's written here is that the domain can be thought of as the x values resulting from smashing the graph of f of x into the x-axis. So if we just, smushed this graph down, flattened it out onto the x-axis, that would give us the domain. And in a similar way, if we flattened it over to the left, right, flattened it against the y-axis, that would give us the range. So that's kind of a neat idea. And I think it kind of comes up in the second half of it here as well. If you're looking at this function, f of x y equal to the square root of 9 minus x squared minus y squared, then, well, I mean, there's a lot of ways to think about it. And he did an example very, sign in link. It's a sign in link. Are you signing into the Google Docs, Max? Curious, yeah. I'm not familiar with. There is a yeah. Don't worry about it. Yeah, I just take attendance. I do have people sign in for office hours. So if it's office hours, I will definitely give you a link to sign in on the Google Doc. But here I do it using Canvas. So no worries. You don't need to sign in. I think Grant does have people sign in though. So yeah. So then if you look at this kind of second example where you've got a function of two variables, square root of 9 minus x squared minus y squared, which is very similar to the function did in class today, which is the square root of 25 minus x squared minus y squared, then we can see that the domain, well, if you solve this inequality, 9 minus x squared minus y squared is greater than or equal to 0. If you add x squared and y squared to the right side, you get x squared plus y squared less than or equal to 9, which is just the inside of a circle of radius 3. But again, if you think about it kind of the same context as this problem, we could literally think about taking this surface, the top half of this sphere of radius 3, and smashing it down onto the xy plane, and that would give you the entire domain. Same idea as how the previous function, we smashed it down onto the x-axis. So that's kind of one visual way to think about what the domain of a function is. In one dimension, if you smash it, or sorry, a function of one variable, if you smash it onto the x-axis, that's going to give you your domain. A function of two variables, you have to smash it down onto the xy plane and see what part of the plane is your domain. All right, so let's look at some examples. Let me stop sharing there. Let me move things around just a tiny bit. Pin my video. Yeah, okay. So here's a couple examples. Also, someone asked me about uploading videos in a higher quality. I will start doing that starting today. So hopefully if you're watching the video recording later, the quality, it will be better than it was for the first video. But let's look at this first one. So here's my function, square root of 6 minus x. Right, we're just doing another function of one variable example just to make sure we've really got a handle on it. So here we're going to say 6 minus x is greater than or equal to 0. And I'm just going to isolate x and say that x is going to be less than or equal to 6. So my domain is everything less than or equal to 6. So here's 6, and here's everything less than or equal to it. And really, you could think of, if you wanted to actually graph it, right? My graph would be this function, right? This square root function looking like this. And I'm just smashing it down onto the x-axis to see what the domain looks like. So here my domain is everything from negative infinity up to 6. Here's a different question. So now we have a function of two variables, and again, we're asking what's the domain of this function? We still need the same sort of requirement, right? That the insides of the square root are non-negative. So I'm going to say, all right, I know that I need x minus y minus 2 to be greater than or equal to 0. For me, I would isolate y because I know how to graph y as a function of x. So I would probably add y to both sides and say, okay, x minus 2 is greater than or equal to y. So I'm going to graph y equal to 2. Sorry, x minus 2. Right, if you've got an inequality, just make it an inequality to graph kind of the boundary of your domain. So x minus 2 has, let's see, a y-intercept of -2 and x-intercept of +2. So I'm going to graph that line. Oh, I'll do not a great job of it. Let's just move these up a little bit. Sometimes things don't always work out perfectly. Okay, so here's the line, y equal to x minus 2. Okay, here's the thing about lines or boundaries in general. Typically, when you're finding the domain, you get everything that's on one side of the boundary. So our domain is probably either everything that's over here or everything that's over here. So let's pick a point on one side and see if it works. Let's pick the origin. Let's pick 0, 0. So if I pick 0, 0 and plug it into this inequality, is it true, or this inequality, right? Is it true that 0 minus 0 minus 2 is greater than or equal to 0? No, it's not. -2 greater than or equal to 0, that is not the case. So 0, 0 is not in the domain, which means everything on this side is not in the domain. It means everything on this side is the domain. So really, this is probably the best way to think about the domain, right? It's telling us the most information about it. What else do I want to say here? We can also write the domain, but it's not particularly informative. Here's the most official, correct way of writing the domain. In this particular example, the domain is the set of all points x, y such that this inequality is true. I would probably write it as y is less than or equal to x minus 2. Okay, that doesn't really tell us anything that we didn't already know, right? We're still trying to say that this inequality is true. But actually graphing this picture and saying, okay, it's everything over here is correct. Now, if on web work, if someone said to describe the domain of this particular function, they give you a bunch of options like, it's the upper half of the plane, it's the lower, like the correct answer would be it's kind of half of the xy plane, right? It's this half, right? It's not a very specific answer, but a lot of times the web work will be like, you've got kind of all these options, like it's the inside of a circle, it's the outside of a circle, it's this part of the plane, it's that part of the plane, it's just a line. So those are often kind of your multiple choice answers when you're trying to do a domain kind of question in web work. And let's also talk about the range while we're at it. So for the range, it's a good thing to know. Whenever you've got a function that's the square root of something, it can never be smaller than 0. Right? Square roots always spit out non-negative numbers. They never give you anything negative. So the question you have to ask yourself is, can you actually get the smallest number? Is there a way that this will actually equal 0? Well, yeah, I can definitely get the square root of x minus y minus 2 to equal 0. I usually like to do kind of a mental check and say, okay, if x is 2 and y is 0 and then minus 2, 2 minus 0 minus 2 is 0 and the square root of 0 is 0. So yeah, we can definitely get 0. And then usually a square root function can get as large as we want it to. Sometimes that won't work depending on how x and y interact with each other, but here it totally will. Because here you could, for example, say, I'm just going to say y is 2. So if I said y was equal to 2, for example, then x could be anything. So if x is anything, then, well, certainly, right, I just got the square root of x at that point. As x gets bigger and bigger and bigger and bigger, the square root of x also gets bigger and bigger and bigger. So a lot of this range stuff specifically is kind of asking yourself, okay, what can I do to make this thing as small as possible? What can I do to make this thing as large as possible? Those are the questions you really want to ask yourself when you're thinking about the range of a function, and also kind of the domain as well. Yeah. let me think for 1 second. We could draw this. So the other thing, might as well. The other thing you're often going to be doing with these functions is drawing level curves. So here's my function. F of x, y equals the square root of x minus y minus 2. And we want to draw the contour map, right? We want to draw the lines that are all at the same elevation. So we're going to pick different elevations. Now, there's kind of a, let's actually do it. We're going to do it the long way, and then we'll talk about doing it the fast way. So I want to draw the level curves or the contours, whatever you want to call them, for c equal to 0, plus or minus 1, and plus or minus 2. So we're going to draw 5 level curves. Let's see what, so all this does is, when we say c, we're going to set the function equal to those values, right? We're setting the elevation, the z value, equal to whatever the level curve value is. So let's see what we get. When I get 0 equal to the square root of x minus y minus 2, I'm going to square both sides. I'm going to get x minus y minus 2 equal to 0. And then I'm going to add y over here. I get y equals x minus 2. So on my xy plane, at elevation 0, I get y equal to x minus 2. So there's my level curve for c equal to 0. And now, so you might already notice it's going to be kind of annoying to keep doing this, right? If we say, okay, now I'm going to say c equal to, let's just group plus or minus 1 together. So I've got plus or minus 1 equal to the square root of x minus y minus 2. I'm going to square both sides. Plus or minus 1 squared is going to be positive 1. And then I'm going to add y. I'm also going to subtract 1. We get y equal to x minus 3. Okay, so y equal to x minus 3. That's going to be down 1 more. So it's going to look like this. Whoa, except, wow, that is the least straight line I've drawn in a long time. Let's try that again. Sorry about that. I was trying to draw parallels, the problem. Yeah, it's a little better. Terrible. So here is both c equal to 1 and c equal to negative 1. Let's also do c equal to plus or minus 2. I'm running out of other colors. Let's use black again. So I'm going to do c equal to plus or minus 2. I'm going to get plus or minus 2 equal to the square root of x minus y minus 2. And I'm going to square both sides. I'm going to get 4 equal to x minus y minus 2. And get y equal to x minus 6. So it's going to be a bit more ways down, right? I've got negative 1, 2, 3, 4, 5, 6. So those are some of the level curves. So what does this thing look like? So the thing that's kind of hard about this is graphing this surface is a bit challenging. I don't know. Let's see what we get. So I will say, we can definitely observe that the larger c gets, the further we're going to go, right? We're going to keep getting lines that are more and more this way, right? Because we're going to get a bigger value over here every time, which means you're going to get y equal to x minus something even larger every time. So we're just going to kind of shift down that way. Honestly, what I would probably actually do if I was trying to see what this looks like is I would look at Desmos. Oh, so I'm going to use my 3D Desmos link. Let's see, where'd you go? Graphing, 3D graphing. Let's take a look. So here's that 3D graphing link. It is in Canvas if you want to ever play with it. So I'm just going to try and graph the square root of x minus y minus 2. Okay, looks kind of funky. You can use these things to kind of turn it around. Okay, that kind of helps me see what it looks like. You guys kind of see that, hopefully. Kind of looks like that. So like this line here, right, that line there, that's your That's this line here. That's your y equals x minus 2. Oh, did I not? Oh, I didn't share my screen. Smart. Sorry about that. So here's the function, square root of x minus y minus 2. And you can rotate it around to kind of see how things look. So here's kind of the normal orientation, right? Here's the x-axis, the y-axis, right? And of course, the z-axis. So this is your x pointing at, like this is your xy plane. So in fact, let me move it around even more. Let me do this real quick. Sorry. I know it's super helpful. Need a little bit. Oh, come on. Now I'm having problems. Need a little perspective here. So if you ever get this thing like twisted, you're like, oh, wow, it's really kind of out of whack. You can still kind of see now. I know I've, right, oh, come on. Really? So sometimes when the thing is like, okay, that's funky looking, you do that, you reload it because you've gotten yourself in a place that you're like, ugh. Right, so anyway, you can kind of take a look at it. So you can see, right, like you can kind of, so I should also mention, right, this actually isn't showing the z values that are negative, right? So if I was going to try and graph this, let me stop sharing here. Here's what I'm kind of seeing. I'm seeing, yeah, let's go ahead. So right, here's my right, here's my y equal to x minus 2 line right here in the xy plane. And then if I go up 1, right, where c equals plus or minus 1. So this is where it gets hard to graph, right? I go up 1, and then my new line is going to be like, right, like I can't draw it. I could try to draw it. Basically, the idea is you've kind of got these lines that are kind of coming. Now, my drawing skills are not super great for this, but it's also going down as well. Yeah, I'm it's not one that we usually graph. So anyway, hopefully that kind of helps a little bit. Maybe I wonder if the GeoGebra graphing thing is any better. Let me take one. Sorry, let me look at one more thing real quick. I don't actually have that. That's fine. Anyway, let's do some more examples. I got a whole bunch of examples here. A lot of them are going to have square roots or logarithms because those are things that have, natural domain exclusions. But let's look at something like f of x, y equal to 1 over y minus x. And let's just stick to domain and range for now. We'll come back and do a few more with a few more level curves a little bit later. So for this one, my domain, well, I can't have division by 0. So I can't have y minus x equal to 0. So I need to exclude y equal to x. Okay, that's not terrible. So here's my domain. It's everything except for the line y equal to x. So if we're trying to draw a domain and we don't want to include a line or a boundary, we typically draw it dashed like that. So my domain would be everything except that line. Okay. What about the range? Well, again, for the range, we need to think about what z values or function values can we attain. And so again, this is where I'm going to do something like I'm going to set x equal to 0, just to make it easier to kind of think about what I might get. So if I set x equal to 0, then my function, often we write, when you actually pick a value for one of the variables, we can write this as f of 0 comma y, because we're setting x equal to 0. That's just going to be 1 over y. And 1 over y can actually equal anything except for 0. So if you set this equal to, right, some number c, then I can say, well, look, if I solve for y, 1 over c equals y, I can get any c value by letting y equal 1 over c, except for 0, because 1 over 0 is undefined. So we can get any z value, c value, whatever you want to call it, by setting y equal to 1 over z and x equal to 0, except for 0. We can't get 0 here, right? There's no way for well, I should say, there's no way for a fraction to equal 0 unless the numerator can equal 0. And definitely the numerator here is always 1, so it can't ever be 0. So the range here would be every real number except for 0. All right. Let's do a few more examples. So let's see here. Let's look at something similar to what we did in class today. F of xy equal to the square root of x squared plus y squared minus 4. So as usual, we got a square root. We're going to set the inside to be greater than or equal to 0. And typically, when you're dealing with domain and range stuff, and I know I said this last class, I think I said this last class, I definitely will say it again if I didn't for the first time. You want to treat x squared plus y squared as kind of one unit. You want to keep it together almost all the time. And then you usually want it by itself, meaning I would love to rewrite this as x squared plus y squared is greater than or equal to 4. Now, as I said earlier, when you've got inequalities, you want to just kind of pretend like it's an inequality. So what I'm really thinking of is I want to think about x squared plus y squared equal to 4. Oh, I know what that is. That's a circle of radius 2 centered at the origin. Now, I'm going to draw my boundary, and I'm going to draw it with a solid line, not a dashed line, because I know I want x squared plus y squared to be greater than or equal to 4. Since I want it to be equal to 4, that's perfectly fine. So let's draw my circle of radius 2. And I really should point out every point on this circle is in the domain of this function, right? The point 0, 2 for sure is in the domain, because if x is 0 and y is 2, 0 plus 4 minus 4 is 0, and you can take the square root of 0. Or if x is 2 and y is 0, or if x is negative 2 and y is 0, right? Or any of the other lots of points on, right? This point here, this would be the point, I don't know, maybe it would be, yeah, the point square root of 2 comma negative square root of 2. At that point there, also in the domain, because if you plug in square root of 2 for x and negative square root of 2 for y, you get 2 plus 2 minus 4, which is 0. Now, we have to figure out, is the inside of the circle the domain we want, or is the outside of the circle the domain we want? Well, that's always where you're just going to test a point. I'm going to test the origin. I almost always test the origin. Usually the origin is super easy to test. So let's ask ourselves, does the point 0, 0, does the 0, 0 satisfy this inequality? No, of course not. 0 squared plus 0 squared is 0, which is not greater than or equal to 4. So since this point doesn't satisfy the inequality, all the points inside the circle don't satisfy the inequality, right? You can pick another point, 0, 1 also doesn't satisfy it. Negative 1, 1 also doesn't satisfy it. Right? Any point inside the circle does not satisfy this inequality, which means all the points inside the circle are not in the domain. So the domain here is all of this stuff out here. If you wanted to describe the domain, you would say it's all the points on and outside the circle of radius 2 center of the origin. Or if you wanted to write it in the more kind of mathy way, you'd say the domain is the set of points x, y, such that x squared plus y squared is greater than. But it's certainly more interesting and nicer to say what it really is. I mean, what it is with all these points. All right, let's talk about the range. So when you're talking about the range, you want to think about the domain. I think I got it right. Yeah, most of this stuff. So here's what we have. We want to know what the condition on x squared plus y squared minus 4, the square root of that. We want to know what this is in between. Well, here's what we have. We have that x squared plus y squared minus 4 is definitely greater than or equal to 0, right? That's the condition that we got to. So if you pick any point in the domain, it's true that this thing here is greater than or equal to 0. This one's actually not too bad, right? So if we start with x squared plus y squared minus 4 being greater than or equal to 0, it's also true that x squared plus y squared plus 4 is unbounded, right? You can pick larger and larger and larger values of x and or y and make this as big as you want to. So this can definitely get up to being as big as infinity. But then take the square root of both sides. Which I know might seem silly, but it's necessary. So the square root of 0 is less than or equal to the square root of x squared plus y squared minus 4. Is less than or equal to this, sorry, less than, not less than or equal to, we can't equal infinity. Less than the square root of infinity. Oh, so I've got 0 less than or equal to my function. So look, my function, f of x, y, is bigger than or equal to 0 and less than infinity. So my range here is 0 inclusive to infinity. Right. Look at some more examples. My thumb kind of hurts. See what time is it? Okay. We'll do a couple more examples and then we'll do a few more little curves. Yeah, we'll do that in a second. Now let's do this one. Let's look at f of x, y equal to the natural log of 9 minus x squared minus y squared. Okay. Yeah. So again, domain and range. Domain. 9 minus x squared minus y squared needs to be strictly greater than 0, right? Because it's the logarithm, the insides have to be non-negative. Sorry, they have to be positive, strictly positive, right? Not 0 or negative. Again, we're going to group x squared and y squared together. So I'm going to rewrite this as 9 is greater than x squared plus y squared. We know that x squared plus y squared equal to 9 is a circle of radius 3, center of the origin. So if I'm going to start graphing my domain here, I definitely need to graph the boundary, but I know I don't want to include it because I want x squared plus y squared to be strictly less than 9. I don't want x squared plus y squared to equal 9, which means I don't want any of the actual circle. But it's still going to act as my boundary. So I'm going to draw it dashed like that. And then again, we ask the question, do we want the insides or the outsides? So pick 0, 0. Does 0, 0 satisfy this inequality? It does. 9 is greater than 0 squared plus 0 squared. So everything inside, but not including the edge of the circle or the boundary of the circle, is the domain. How about the range? Good question. So here's how I want it. So basically, I'm kind of thinking about what's going on with this. I know that 9 minus x squared minus y squared has to be greater than 0. That's the domain that we started with. It might help me. In fact, let me actually rewrite this a little bit. I often find it helpful to, instead of writing it as 9 minus x squared minus y squared, to write it as 9 minus the quantity x squared plus y squared. In fact, let me back up even further. I really find it helpful to start with this. I know that x squared plus y squared, I need it to be less than 9. But we also know something, and he said this in class, and this is very worthwhile. It's always true that x squared plus y squared is greater than or equal to 0. Because they're both positive or non-negative things. If we add them together, they're still going to be non-negative. But now what I want to do is I want to manipulate this to make it look like that. So I'm going to multiply everything by -1. When you multiply inequalities by a negative, you change the direction. So I'm going to have a -1 times 0, which is 0, bigger than or equal to -x squared minus y squared, bigger than -9. I multiplied everything by -1. I changed the directions of my inequalities. And now I'm going to add 9 to everything so that I can get my insides to look like this. So I add 9, really to look like this, I should say. So 9 plus 0 is bigger than or equal to 9 minus x squared minus y squared is bigger than 9 minus 9. I will say, you probably could have worked this out a different way, right? You probably could have said, well, I know this has to be bigger than 0. And I also know that since, right over here, I also know that since x squared plus y squared is at the smallest 0, right, then the biggest this can be is 9. Because the biggest 9 minus something that's non-negative can be is when it's 9 minus 0. So often we think about making this expression as big as possible by making the thing you're subtracting as small as possible. And we make this thing as small as possible. Well, really, this could be a lot smaller, right? 9 minus x squared minus plus y squared could be like infinitely negatively small, right? It could be like -1 billion, whatever. But we know it has to be greater than 0 because of the domain restriction. So then I'm still trying to figure out what's going on with my function here. So I'm going to take the natural log of everything. I'm going to say, all right, the natural log of 9 is bigger than or equal to the natural log of 9 minus x squared minus y squared is bigger than the natural log of 0. So here's the thing. We're between 9 and 0 here. The natural log of 0 is not a real number. It's totally undefined. But we know that if you're getting very, very close to 0, the natural log function is getting negatively infinitely large. Essentially what I've done is I've said, we'll erase this here. As I've said, our values are between 0 and 9, and now we're taking the natural log of those values. Well, I know what the natural log function looks like. There's the natural log function. And if we go over here to 9, there's 9 comma natural log of 9. So my domain, for lack of a better word, was 0 exclusive to 9. And my range is everything from -infinity up to natural log of 9. So that's our range here. inclusive of natural log of 9. Okay, let's do a couple of examples that include some level curves. But I should stress, when you're thinking about domain and range, you're really just trying to think about, well, especially for the range, you're really trying to ask yourself the question, okay, what can I do to make this thing as big as possible? What can I do to make this thing as small as possible while still obeying the domain constraints? Let's look at this next example. And we'll do some level curves as well. And somebody asked in class why his level curve had like a natural log. I will totally explain that right now. It's not anything super sneaky or anything. It's just like, you'll see. Let's say our function is e to the square root of x minus y squared. Okay, I want to find the domain. So I know that the insides here have to be greater than or equal to 0. Usually I would solve for y, but I really wanted to solve for x. So I'm going to say that x is greater than or equal to y squared. Well, great. We know how to graph x equal to y squared. It's just a parabola that opens to the right. Or you could do the silly thing and say it's y equal to plus or minus the square root of x, but this is easier. All right. Now here's the thing, we can't pick 0, 0 because 0, 0 is on the boundary. And so I need to pick something that's not on the boundary. So let's pick the point 1, 0. So if x is 1 and y is 0, are we satisfying this inequality? Yay or nay? We can use the reactions. How exciting. You don't have to, but you could. You guys are like, nah, we're good. Also, while I have a second here, let me do one quick thing. Man, there's so many of you guys. I'm glad there's so many of you. Like, it's not a complaint, just it's a lot of names to screenshot while I try and get the attendance taken care of. Okay, I think I got everybody. So, nobody knows at this point satisfies this inequality or not. So if x is 1, y is 0. If I plug in 1 for x and 0 for y, is this good or no?
Yes, it is.
It does.
Cool. Yes. Thank you. Right. If x is 1, y is 0, definitely 1 is greater than or equal to 0. So that means not just this point, but literally everything in this part of the xy plane is our domain. And we could write it, right? You could say the domain is the set containing all points x, y, such that x minus y squared is greater than or equal to 0. I don't think you need to do that though. I really think Professor Lewis is going to be more interested in you being able to think about what the domain looks like. Let's talk about the range. So, okay. So I'm thinking about this square root, I'm thinking about x minus y squared first of all. I know that x minus y squared has to be greater than or equal to 0. And I know that it's also can be as big as I want it to be, right? I could set y equal to 0 and let x range to infinity. All right, then we can take the square root of everything. Square root of 0 less than or equal to the square root of x minus y squared. Wow, that looks beautiful. Less than the square root of infinity is still infinity. So there's 0 less than or equal to the square root of x minus y squared less than infinity. And then we're going to raise everything to the e power, or we're going to write everything as the exponent of e. We're going to exponentiate everything. So e to the 0 is less than or equal to e to the square root of x minus y squared is less than e to the infinity, which is still infinity. Okay, so look, our domain, sorry, our range, our function f of x, y is bigger than or equal to 1 and is less than infinity. So our range here is 1 to infinity, inclusive of 1. So my kind of tactic for dealing with the range is kind of trying to start with the inequality I know is true and then kind of work backwards to get back to the function. So that I can say, oh, if I know that if this part's between 0 and infinity, then I can do stuff to all parts of my inequality to get to figure out what e to the square root of x minus y squared has to be between. Hopefully that makes a little bit of sense.
Do you think that strategy is viable for like most examples we'll come across?
I do think it's viable for most examples. Maybe not all, but certainly quite a few.
Okay, thank you.
Let's talk about the level curves of this. So the way you find the level curves is, again, you're trying to find the curves that are all at the same elevation or the same function or z value. So we're going to set the function value equal to just, some people use c, some people use z, it doesn't really matter. But instead of like doing it value by value by value like we did in the first example in class today, we're just going to say, I'm going to solve for z. I'm sorry, I'm going to just start with z. And really, people often use a c value here so that they recognize that this is just a constant value that we're going to change at our discretion. So now I'm going to try and rewrite this in a way that makes it easier to think about graphing the actual level curve depending on what this value of c is. Now, we also know, because we've talked about the range already, we know that our value c has to be in the range, right? There is no other choice. So when we're talking about drawing the level curves here, we're going to pick values of c that are in the range of the function. So let's see here. Let's take the natural log of both sides. So the natural log of c equals the natural log of e to this is just the square root of x minus y squared. Let's square both sides. So natural log of c quantity squared is equal to x minus y squared. And then if I solve for x, I get x equal to y squared plus the natural log of c squared. So then here's what we do. In fact, let me show you on Desmos, so I think it'll be a little bit easier. Let me actually share my screen this time, not just pretend to share my screen. Let's go to Desmos for real. Why am I doing it? Okay, Desmos. Sure. So what's cool about this is you can actually even throw in the c as well. So let's say we want x equal to y squared plus the natural log of c. Yes, I'm going to add a slider, but I want that quantity squared. Do you make sure you put the square on the outside? If you put the square on the inside, it'll be wrong. Okay, so look, there's c equal to 1. There's your level curve for c equal to 1. But if we go c equal to 2, well, look, the level curve moves a little bit to the right. I think there's a different, I think there's another, yeah, cool, I can do it that way. So the lowest c value is 1. And then let's go up to like 20. And let's take the step 1. So that way, sure, we can just kind of click over. So we can see that as we go, okay, come on. As you go over, right, each time you go over, it's just moving that parabola a little bit to the right, which makes sense, right? Because that's really what you've got here, is just a shift to the right. Right, when x is a function of y and you add something on the outside, you shift it left and right. So this kind of shows you what your level curves are. And if you really wanted to, you could then kind of, I feel like there's got to be an easier way to do this, but you could kind of take, let's just do it this way. We could graph a whole bunch of them at once if we wanted to kind of see. Sure, yeah, I know it's stupid. Let's graph like 4 of them, and then let's just pick some different values of c. It's kind of cool. You can make some level curves. So there you go. You can kind of see what the level curves are. So that as your c values go higher, your parabolas move further right. So if you're going to try and graph this thing in 3 dimensions, stop sharing. So graphing this thing in 3 dimensions, now it's going to be kind of terrible because it's coming out at us. Right, but like, so here's 1, 0, 0. You got like a parabola coming out that way, and then it would kind of do this deal. So you've got like more and more parabola. Gosh, like my graphing skills are terrible. If I rotate it, so if we rotate the axes so it's a little bit easier to see, if we rotate it 90 degrees that way, so this is your x-axis, and back this way is your positive y-axis, then it becomes a little bit easier to be like, okay, it's going to look like that, and it's going to kind of do this thing here, and you're going to have all these level curves that are parabolas opening to the right. Hopefully that's a little bit easier to kind of actually see what I'm talking about. But the thing I wanted to point out is that, I know I just erased it here. That's where that natural log came from. Basically, instead of just picking a c value over and over and over and over and over again and solving this equation many times, we just solve it once. We're like, okay, I'm going to say that x is equal to y squared plus natural log of c squared. Or they might use a z there instead of a c, and then just pick different values of z or c to get different level curves at different elevations. Let's look at one more example. Also, I do have office hours after this. There will be a different Zoom link, so I will have to close this one. But if you want to come to office hours, you're all welcome to. Yeah. So let's see here. Sure, let's do this one. Let's say my function was, I'm going to do this one quick because we only got 3 minutes. 6 over x squared plus y squared plus 2. Domain, there's no issues, no square roots, no logarithms, and there's no way we could be dividing by 0 because the denominator is never equal to 0. Right? X squared plus y squared is always greater than or equal to 0, plus 2 is always greater than or equal to 2. So we know already that x squared plus y squared plus 2 is in fact greater than or equal to 2. Okay. So the domain here is not all real numbers. The domain is the entire xy plane. Okay, how about the range? Well, it's good to observe this. It's going to help us. So we know that x squared plus y squared plus 2 is in fact greater than or equal to 2. And it's also, I suppose I should say, it's less than infinity. You do really kind of want to have a compound inequality here. I kind of want to write it the other way though. Usually I like to have the smaller things on the left and the bigger things on the right.
Can you explain how we know that?
How do you know what?
To like that thing you just wrote. It's kind of confusing how you got there.
Sure. I started with this. X squared plus y squared is greater than or equal to 0. Then I added 2 to everything.
Oh, see. Oh,
I see. You're just trying to make it like the function itself.
Right, exactly. So, and I kind of was saying that specifically about the domain. I was like, oh yeah, I know that this can't be 0 because I know that it actually has to be always bigger than or equal to 2 because of how the expression is. But then I also noticed, oh, this is going to help me work with my range because I want to figure out how this is bounded. Well, I know how this part's bounded. It's bigger than or equal to 2 and it's less than infinity. And now I'm going to take the reciprocal of everything. So the reciprocal also changes the direction of the inequality. Got to take the reciprocal. So 1/2 is bigger than or equal to 1 over x squared plus y squared plus 2 is bigger than 1 over infinity, which is 0. I should point out, this does make sense, right? If this part here is bigger than 2, let's say it was 3, then it's definitely true that 1/2 is bigger than or equal to 1/3. So it checks out. And now we're just going to multiply everything by 6. So multiply this by 6, and 6 times 1/2 is 3. Multiply this by 6, you get 6 over x squared plus y squared plus 2. Multiply this by 6, you still get 0. So our range here is 0 to 3. Exclusive of 0, inclusive of 3. I know we're out of time, but let me just talk about the level curves for like a hot minute. So if I was going to find the level curves, I would say, all right, I'm going to set 6 over x squared plus y squared plus 2, right, the function equal to some constant value. And then I'm going to try and solve for it in some way that makes sense to me. I see an x squared plus y squared. I'm thinking I'm going to have a circle somewhere. Let's reciprocal both sides. So it looks like x squared plus y squared plus 2. Oh, sorry, reciprocal both sides, you foolish man. So x squared plus y squared plus 2 over 6 equals 1 over c. Multiply both sides by 6. And then subtract 2. So x squared plus y squared equals 6 over c minus 2. We know the range for c, right? C has to be between 0 and 3. So look, this is going to give me a circle centered at the origin. And the radius is going to be the square root of 6 over c minus 2. So like if I was trying to draw the level curves, right, if c was equal to 1, I'd get 6 over 1, which is 6, minus 2 is 4, square root of 4 is 2. So for c equal to 1, I get a circle of radius 2. And then if c is equal to 2, 6 over 2 is 3. Wow, these numbers work, this example worked out very nicely, I got to say. 6 over 2 is 3, 3 minus 2 is 1, square root of 1 is 1. So if c equals 2, that's going to be a circle of radius 1. So it looks like as the elevation gets higher, the circles get narrower. So if I had to guess, well, again, we can only go up to as high as 3, right? So c equals 3, you're going to get a circle of radius 0, because you get 6 over 3, minus, which is 2, minus 2 is 0. So it looks like we have, I don't know exactly how this looks, but it probably looks something kind of like, sorry, I was a little bit careless there. If you let your c values get smaller, or like if c is like super duper small, like 1/10, 6 over 1/10 is 60. 60 minus 2 is 58. That's a big circle. So if you get small values, you're going to have really, really small, big circles. So let's say we probably have something like this. And it's kind of like doing that and coming out at you. You've got like these circles that are level curves. That's kind of what's going on. I know it's not, so I have to apologize in advance for the rest of the quarter. My we don't do a whole lot of 3D graphing, but my 3D graphs are not excellent. I apologize. It's not a skill that I have been great at developing. But what I will say here is that when you're finding the level curves, so if someone said, like, I want you to draw the level curves for c equals 1, 2, 3, 4, 5. Solve the equation. And so when I say solve, you have to kind of use common sense. You have to be like, okay, I want to make this something I know how to deal with. Oh, I see x squared plus y squared. I'm going to isolate that because it's probably going to give me a circle. Or